Swayam Prabha. Digital India. Educated India.
Today, we will focus on this topic, which is the strut and tie models for the design of reinforced concrete structures. And actually, let's try to frame the problem. So we know that concrete has a good compressive strength, whereas it does not have good tensile strength capacity. So wherever, according to our structural analysis, we do find that there are tensile regions in our structural elements, well, we know that concrete is expected to crack, and in the tensile regions, we put reinforcement. When you have a cracked member, you see the cracks disrupt the continuity of your element. It's no longer an ideal homogeneous solid, but it's made by a compression zone, which is generally concrete, a tensile zone, which is the reinforcement, and they are connected by the solid parts of concrete between the cracks. So this leads us to think, if we look at the element, that was when Morsch and Ritter looked at the cracked beam in shear, they said, okay, this looks really like a truss. So you visually can see the truss. So the truss models were used to design the reinforced concrete structural elements. As a matter of fact, we have to distinguish in a structural element the zones according to the characteristic of the stress field. In an element, there are regions where, as you can see here, the stresses and strains are distributed so regularly that you can have a mathematical model which describes them. And these are called the B regions, where B stands for beam or Bernoulli. It's where we do apply the beam analogy, the beam model, because it works there. That region of the beam has the characteristics to respect and fulfill the beam model. For example, think here of this beam, okay? Well, you have this beam with these loads. The diagram of the bending moment is this one, and the diagram of shear is this one. If you draw the tensile and compressive stress flow lines, you see these dashed lines are the tensile stresses, and these compressive lines are the solid line are the compressive stresses. You see that in this central region, the stress lines are very regularly distributed. So here, you can really apply the beam analogy. Well, you can apply also otherwise, but there is. But think of a beam like this. So first of all, look at the dimensions. We have a beam which is about 10 meters long and 3 meters deep. So the span to depth ratio, the slenderness, geometrical slenderness, is around 3. And we do know that 3 is a limit above which the beam model works pretty well, but below which the beam model starts not working well. But it's not only this. You see, we have here a load, a point load. So if you look at the span here on the right side, the span is about 4 meters. The ratio between the span and the depth on this side, it's about 1.5. And the ratio on this other side is about 2, sorry. Also, you have an opening here, which further complicates things. You see the stress distribution lines. From here, the load must go to the supports. But in order to do that, well, here is more or less regular on this side. But here it has to go around the opening and be conveyed back. And also here, the stress lines when they meet the opening, they have to turn around it, or they are forced to flow into a very narrow region. So in this region, where do you can apply a beam model? I would hardly say nowhere. So in contrast to the main, regular region of a structural element, which we call the B regions, where there is a regular pattern of stresses and strains, and we can apply the beam model, there are regions which are subjected to very strong gradients of the stress and strain field. These regions are called in the code terminology as D regions. Well, you can say D stand for detail, disturbance, discontinuity, whatever word with D you think may apply to that. And in a structural element, you may have several of them. A beam column joint, solid joint, the end regions, the corbels, which are quite common in precast structures, the regions near a concentrated load. As we were seeing yesterday when we spoke about the lifting, I said, well, leave a region equal to the depth of the beam on either side of the lifting hook, because that has to be detailed with care apart from the rest of the beam. And where you have recesses or holes, you can have also in some precast structures, well, some holes can be just because you want to lighten the weight. You remember we had the picture of that very long span beam, double touched, with holes in the middle, close to the mid-span. They were on the web. The web we know that carries the shear, and close to the mid-span, the shear is negligible or is very small. So there is a place where you do not need the material. And so they made the hole for aesthetical purposes and so on. But in other cases, you might have holes and so on to have some pipings and ducts to pass through. And you make in parts of the element where you do not risk to have, disturbances statically. So you see some examples here. So here we do have a beam column corner. All these, part here, which is, filled with this, is a D region. Here we have recesses. You might have, you remember we saw in some pictures for the beam which were continuous over the support, and then they had some ends, to connect to the other beams. Here you might have some change in the depth of the beam. You might have a hole. This is an element. This element here is an isolated footing, is by itself a D region as a whole. So you hardly can design a footing element employing the beam theory. It does not apply to it. So when you speak, if you have a footing element like this and you speak about moment and shear, there is no meaning, because moment and shear, axial force, torsion moment, and so on, what are they? They are, in a sense, some average stresses over the cross section. And we can calculate them because according to the beam theory, if the beam theory does not valid, we cannot calculate, properly speaking, from the mathematical point of view, we cannot calculate the bending moment and shear. So there is no meaning in an element like this to speak about moment and shear. So likewise, there is no meaning to speak about moment and shear in a corbel. Well, you can have something which is similar to that. You can say, okay, at this position, I will have a moment effect or a shear effect. But from the structural point of view, from the beam theory point of view, concepts like moment, shear, and so on, they do not apply to D regions. Because there you don't have the patterns of strains and stresses, which is so regularly distributed, so that the hypothesis of the beam theory can apply, and you can use the mathematical tools of the beam theory. And you see another example of an element which is a D region as a wall is a deep beam. If the depth of your beam is very high and the span of your beam is not at least 3 times longer than the depth, you cannot speak about a beam in this sense. Well, there are other examples. This is, you know, when you have to build a new building, you have to excavate it, excavate the site to make space for the foundation. But especially if you are doing it in urban areas, then you must be sure. But anyway, you have to consolidate the side of the excavation, the walls of the excavation, to avoid any kind of issues that this slides down, that you make disturbance and so on. And so sometimes you need also to consolidate the soil, and you do drilling a hole and putting some tendons. You apply tensile force and then you inject. Well, this concentrated force here, imagine that this is a very deep beam with a lot of concentrated forces applied. So all those regions where you have the force, these are the regions that you have to design. So it's not only in, you know, building structures and so on, but also in this kind of geotechnical application. And this is an example. You see, these are the pre-stressing tendons that are arranged according to these 5-point shapes. So the first thing is, okay, but we have understood in some way the criterion to check whether there is a D region or not. But how do we identify, most of all, how do we identify its sides? Because we must know in a structural element which part is a D region and has to be designed as a D region, and which part we can design. So let's take this example. Okay, we have a column here, and this column, imagine, has a point load in the middle of the top cross section, just there, and is supported. Well, here is a 2D drawing, but it's supported just on the 4 corners on the bottom. So you have this column under concentrated loads. The force applied is F on the top, and by equilibrium, the sum of the 4 forces on the bottom must be F as well. So what we do? We do replace, and we know well that here, the force here must spread to the wall sides of the column like this. We do replace our external actions with an equivalent system. Equivalent means that they have the same resultant and resultant bending moment. The resultant of this force is F, the resultant of these forces is F. We replace with a uniform state of stress. If H is the sides of the column, this stress is F divided by H. Okay? Uniform. If you calculate the resultant of this stress, it's exactly equal to this force. Most of all, this force is in the middle, in the center of the cross section, 0 moment. These forces are symmetric, 0 moment as well. The moment of the distribution of these stresses is 0 as well. So the equivalence must be in terms of resultant force and resultant bending moments. But then, can we say that this structure is equal to this? Properly speaking, not. So in order to bring back the equivalence, what do we have to do? Well, we can apply a system of loads and stresses whose resultant is 0. You see, if this is a force F and I apply here a force, a stress going upward, F divided by H, so the resultant is 0. And the same happens. But if you sum up this and this, you just get back this. If you go back to solid mechanics, there is a fundamental principle, which is the principle of Desaint-Venant. And it states, if you have a solid which has to be long enough with respect to the side of its cross section. At a certain distance from the cross section, you do not feel the effects of really how your actions are applied to the edge cross section. You only feel the effects of the result. So this is a principle of the solid mechanics. You have a solid body with its length, like a cylinder specimen or a prism or whatever. Its length is, let's say, sufficiently longer than the dimension of its cross section. At a certain distance from the cross section, whatever way your loads and stresses are applied on the edges, you do not feel the effects of local distribution. You only feel the effect of the resultant force and moment. And how far from the cross section you have to go? Well, you have to go at a distance from the edge, which is exactly equal to the side of the cross section. That is what the Desaint-Venant principle states. And this allows us to say, okay, what is the resultant of this system of forces and stresses? We have just said before, 0. So at a distance from this cross section equal to the side of the cross section as well, so at a distance h, you actually only feel the effect of the resultant. The resultant is 0, so you don't feel any other effect. So this is the way to identify the sides of the D region. And so this column here will have 2D regions and the top and at the bottom equal to the side of the cross section, and the rest will be a B region that you can design as a B. Well, I can show you this. We made, for this case, a very simple finite element analysis, linear elastic. So you build up your column and you apply a force here, a concentrated force here, and you put some pins here. So you see that this concentrated force first has to spread to the whole cross section. So the patterns of your stresses are like this. First of all, they are inclined, and then they flow regularly downwards. And at a certain point, they must go, this edge cross section is supported only on the corners, then they must go to the corners. So you see that basically there are already some disturbed regions here. But this is the case A. So if you go back to the previous slide, this is the case. Then we made a finite element model for this case. And you see here, you have very regular stress flow lines. If you apply uniform stress, they flow. This is case B, so is this one. Then we model it this one. And you see actually that here, as we said, from a certain distance onward, you don't feel anything more. So basically you here don't have any more stresses. Actually, this drawing here is made, plotting the stresses as arrows proportional to their magnitude. Here you have stresses everywhere, so you see like a continuous line. Here you don't see any more stress. So this yellow region, these regions that we dashed as yellows, actually are the D regions. It's where you feel the effect of the way in which the loads are applied. If you go farther than a distance equal to the side of the cross section, you just feel the effect of the total force, and total force here is 0, so you don't feel anything more. So this is the narrative of the steps that we have set. So first of all, replace the real structure with a fictitious one, which has exactly the same geometry and boundary conditions, but it's loaded in such a way that the Bernoulli hypotheses are satisfied everywhere. And it satisfies the equilibrium condition. Structure like this is a perfect Bernoulli beam. Then introduce a self-equilibrating state of stress. Self-equilibrated means that its resultant is zero. If you superimpose to the fictitious structure, you get back the original one. Apply the principle of Desainvenant, which states that the influence of this self-equilibrating state of stress is negligible at a certain distance. And then you have identified, as we have seen from the example before, the D and the B regions of your structure. And these are other examples. You see, you have this beam supported and with a uniformly distributed load. Well, as we said yesterday, the support reaction has to diffuse to the cross section. There is like an arch mechanism. That region we design apart from the beam. How do we manage this example? Well, we replace this force with a uniformly distributed state of shear stresses on the cross section. And applying the same thing, we just realized that we have to design the end parts of this beam as D regions, and the other part can be designed as a B region. This is a typical example of a precast structural element, for example. So this force here has to undergo a two-way diffusion mechanism because it's applied at the, see, it is applied here. So first of all, you have to bring it to diffuse it to the wall depth of the cross section. But when you arrive here, you have also to diffuse through the wall width of the beam or through part of it. I don't remember who came yesterday with an example of a composite beam column. Okay, yeah, that is something like that. You have this part which is your beam. Actually, your beam was an inverted T because you also had the plane. And then you put the slab on the top. If you make the slab to collaborate with the beam, which means that you must have the reinforcement coming outside, you complete with some casting and so on, then from a certain point onward, you can make them collaborating. So you can have a T or an I cross section. Well, the issue is that also, if you imagine that you have a beam here, then there is a large slab field, and then have another beam, you may not say that the wall width of the slab is collaborating because the diffusion of the stresses is limited. And in the codes, you find some simple relationships that tell you how wide is the collaborating width of your slab. So how part of it, which part of it you can consider to be part of the beam, and which part of it you have to design separately. Here in this case, you see, it's a deep beam. A deep beam, if the span is between the depth and twice the depth, all the beam is a deep beam, is a D region. And when you start going more than 2, you start having a narrower B zone. But in some cases, you see, well, there is not the case to design that, just design as a deep beam. So for example, imagine, we have said, okay, if the length of the element is more than 3, we say 3 to 5 times sometimes the depth of the beam, we can consider as a beam and design accordingly. Well, but it's not only a matter of geometry. Look at this beam. This beam, let's say it's it's long 4 times the depth. But we know that at the edges, always we have a D region equal to the depth of it. And if we have a concentrated load, as we said yesterday, on either side of the load, we have a D region which is equal to the depth. So you risk that a structural element, even if geometrically can be considered as a beam, depending on the loads and on the boundary condition, is actually a set of detailing regions that you have to take into account. This is a very interesting. Okay, so how do we proceed with the design? So first of all, as we said, the most important step, the first step is to understand, okay, my structural element, because of its geometry and because of its boundary conditions, because in solid mechanics theory, we work with the Desaint-Venant solid. The Desaint-Venant solid is a solid which floats in the air and has loads just on the edge cross section, and these loads are in equilibrium. So it's an ideal model, but in the reality, we have the boundary condition. So a structural element has a geometry, but has boundary conditions as well. So because of this structural element, which are its parts that I can design applying the beam model, and which are the parts that after having done this, I have to take care of and to check and detail with a D or strut and tie model. So this is the first step. P regions we know how to design. Then D regions have to be singled out and to be studied separately. And we use in order to design the D regions, the strut and tie model. Why do we call it strut and tie? Well, because as you have seen from the examples that I have also shown, when you have a load which is applied on a structure, that load generates a stress state. And you can always analyze that stress state in terms of principal stresses, which generally are tensile and compressive. So the first thing is to understand which is the stress field. In some cases, it can be intuitive, or you can figure out with, I would not say imagination, but you can figure out with the graphical static, let's say. In some other cases, you need, nowadays we need the finite element analysis. Very simple, linear elastic at this stage. No need to go for complicated analysis. So you identify your stress fields, and what do? You concentrate these stress fields around their center lines. Compressive stress fields are the struts. Tensile stress fields are the ties. And in reinforced concrete, the ties are steel bars, cannot be otherwise. And the struts are regions of concrete. So actually, your strut and tie model then turns out into a model that you can handle, which is a truss. Struts and ties. So you calculate the forces in your struts and your ties, and you dimension them accordingly. There is another thing. You have to design the nodes where the tie frames into the strut, where the strut frames into another strut. So it's not only a matter of designing the strut and the tie, but it's also a matter of designing the node. Well, this is the main difference from, the mechanics model that we have, because there we model our nodes like hinges, and we don't care. The hinges are regions where forces are exchanged. But exactly because forces are exchanged, we have to check that those forces pass from one element to the other properly. Well, as we will see from the examples, the power of the strut and tie models is that not only, we said the ties are bars, because only in reinforced concrete the steel carries the tensile force. And we put the bars in some positions. So you could say, okay, I have made my analysis, I have found the stress field, I put the ties where I do see there are the tensile stress fields. That's true, but it's also the opposite. if you put the tie somewhere, most likely your structure will feel that there is something which is sufficiently rigid and strong to carry the tensile forces, and the tensile stresses will go there. So when you design a strut and tie model, it's not simply that you are complying with the stress fields that come from the analysis. You are, accompanying the structure to behave as you want. So this is the power of this model, that you really govern the way in which the structural element, that structural detail is behaving. If you want it to behave in such a way, design it in that way or in the appropriate way. In English, we use the word design. I don't know which is the word in English or in Tamil, but in Italian, the word that we use for design is progettare. Progettare it comes from the Latin, as most of the Italian language, but really it speaks. I throw ahead of me something. So when I do what I do when I design, I am anticipating something. I am like, okay, say I figured something out. Let's jump ahead with that. And actually, the exact meaning is that I do not only throw ahead of me once. The verb in itself indicates a repeated action. So I continue to think of something and push it ahead of me. So I am anticipating something. It's a really very, very nice word. And this is also because the design is not something, straightforward. Okay, you start from here and you end up solve an equation and you just go to the last page of the book to see if the solution is correct. No, design is a process. There is no strange in adjusting the design. Adjusting because, you may have, you hope that requests do not come in repeated times that force you to adjust too much. But the design can be adjusted also because as long as you proceed with it, you realize that probably there is a detail which can be conceived in another way, which makes the behavior of the structure better. So you adjust the design according to the design process itself. This is something very powerful that we have in our hands and very fascinating, I think. It's the very beauty of our work. It's the creative part of our work. Otherwise, you can say, okay, what is the job of a structural engineer? Just to pick up a code and apply the code. It's not that. The code is a tool. The code is a tool. But we must, feel the structure and accompany it to behave like we want it to behave. Well, we want it to behave in that way because according to our engineering knowledge, we know that that could be the most appropriate, I will not say right or best, the most appropriate way. So look here, for example, these are two deep beams. Okay, this deep beam is supported, and you have a load, is the same load which is applied either on the top or on the bottom. Well, if you would have to use the classic scheme of a simply supported beam with the load, these two situations, you will not distinguish them. The load is throughout. Yeah, it's symmetric. It's simply not. Yeah, thank you for saying it's simply for the clarity of the drawing. Yeah, you have to imagine this load also applied. But if you apply the model of a beam, you do not distinguish these two situations. You don't care about where is the load applied. But we have seen, for example, when we discussed the lateral stability of the beam, that if the load is applied on the top, it tends to be, something which exaggerates the buckling. Whereas if the load is applied on the bottom, it tends to tilt back the beam and so can have a stabilizing effect. So always think that we use models where the beam is alive, but then the beam has its own dimension. And this we will see also when we design, for example, for earthquake, has some consequences. But so, how do we imagine? Okay, here the stress field is drawn, but we can imagine, for example, we have this load applied throughout this width to this span here. How do you imagine it goes to the support? Well, you can imagine that it starts from the wall width you see here, it starts from the wall width, and you starts narrowing it and convey to the support. So you can imagine that here there is a strut. And how do you idealize it? Well, you pick up half this length, you put a force in the middle, and draw a straight line down to the middle of the support. This could be your strut middle line. And the same happens on the other side of the beam. But then you have two inclined forces here. You see the blue arrows. And here, the reaction force is vertical. That inclined blue force has a vertical component, which is equilibrated by the reaction, but there's also a horizontal component, what we call thrust. So you have to put a tie where the right arrow is. And what is the mechanism which occurs in the other beam? Where here you have a load which is hanging down. The reaction force is here, but so you have to form an arch to your stress fields where the tensile forces can be hanged down. You see, that is the principle of the arch suspended bridge. You have an arch which carries the load and you suspend it, the bridge on itself. So there is something which always converges. And actually, these pictures are taken from a historical textbook by Fritz Leonhard. He did really a lot of work on this. And you can realize if you test a beam like this and look at the crack patterns and at the failure patterns, you can really realize that how the strut and tie mechanism is functioning. You see that in this beam here, we have basically two solid parts here. These are the regions where the strut can form and work. And you have cracks where orthogonal to the tensile stress field. You see here that you have this nice pattern of arch-shaped cracks. It means that you have tensile stresses orthogonal to these cracks, but the solid part of concrete between the cracks forms the arches, forms the strut. Well, we have to say one thing. Actually, thinking of the structural element like this, it's very good if you want to visualize what could be the ultimate condition. Serviceability limit state are a little bit more questionable, also because there are some assumptions that we will see that make it surely good for ultimate limit state, but not for serviceability. But so how do we design then our strut model? Because I said, okay, you can perform a finite element analysis. Yes, but sometimes it cannot be necessary, or at least you can start in a different way. So look at that beam. That is a deep beam supported on its edges. And the load applied on top is not uniform as a trapezoidal distribution. Okay. So first of all, you have to calculate A and B forces. But A and B forces, which are the reaction forces, you can calculate with the solid mechanics, consider the beam as a rigid body. So you first calculate A and B. And then you go on the distribution of the load and divide your applied load into two parts so that the right part is B and the left part is A. So this is not the middle. It's not exactly the middle, even if it might look so. Then what do you have to do? Well, you know that this force A has to go to this support, and this force B has to go to this support. And you also know that if there is a vertical load, the stress field will start vertical there. Like at the support, you know that your stress field will have some, boundary constraint. They have to start vertical when a vertical force is applied. Then you connect them, and you connect them with this, curved path. And then how can you have your vertical stress field to bend to follow that curved part? You need some transverse stresses which comply with this shape. So this is the field that you can expect. Then you replace this curved path with straight lines. You see, you have a truss strut which goes up like there and then goes up like there. Another one like this. You have the tie here, and to connect those two, you have this strut in the middle. So this is the so-called load path method. So you figure out how the stresses or how the loads, the applied loads, they go from their point of application to the supports. And you design your strut and tie model, your strut and tie mechanism accordingly. There is one very important concept. What is the shortest distance between 2 points? Actually, the load paths follow lines that then tend to have the minimum length. Yes. We know from solid mechanics that when you have a structure, solid or whatever, under loads and boundary conditions, okay, the configuration of the structure, which is at the same time fulfilling the equilibrium and the compatibility, because these are what is the one which is characterized by the least energy. Now, least volume energy. Now, if we idealize our structure as a series of struts and ties, what is the volume energy? Is the integral of stresses over some cross section multiplied by the lengths. So if we have to minimize the energy, we have to minimize the length of the strut and tie. This is another example. Actually, you can say that this can be the edge cross section of a column where you have the load which is applied with a very strong eccentricity. You see, the load is just at the edge of the cross section. It can happen. You have building because you have different elements that have to be converge on this element, and so they apply different. So what is the resultant of this force? The resultant force is F. But then if we consider it with respect to the center axis of that beam, there is also a bending moment effect. So at a distance from this edge cross section equal to its depth, so you see this is a square, it's not a triangle, you have a distribution of stresses like this. And you can divide this stress diagram into a part, which is this one, you see. This part here is the part whose resultant is equal to F and which equilibrates the force. This other part here, you see, it's B and B, the two resultants are equal. So this part here does not contribute to the force equilibrium. It gives you the moment part. So you can say that this cross section is engaged partly to equilibrate the force and partly to equilibrate the moment. You can think of this. And this is another interesting way. You remember, when you design a column for axial force and bending moment, what does it happen if you draw the interaction diagram? The interaction diagram first increases and then it decreases. So it means that you have at the same time bending moment and axial force. Your capacity is worsened in one case. Each one of them worsens the other. Yes, because if you have a very high axial force, you have to engage a larger part of the cross section just to carry the axial force, and you have a narrower part to carry the bending moment. That is the way in which you can also see the interaction between axial force and bending moment. Yes, yes. Anchor block is eccentrically, that is what you have to deal with. And so, if you have, split your stress diagram. This is the stress diagram, which comes with the same formula that we have seen yesterday, n divided by a plus m divided by flexural module. But we have split our diagram into a part which carries the axial force and the part which carries the bending moment. And we have these resultant forces. So this force F has to go here. You have to connect this. This is the load path. And these two forces, you know, this goes straight ahead back, and this has to connect here. So you see that, oops, sorry. You see that here you have a slight bending, and means that you will have compressive force here. Here you will have a stronger bending, and you have compressive force. And here you have to close your, you know, diagram with a tensile force which equilibrates the horizontal component. So the Strut and tie model, now there is a little bit of formalism. The Strut and tie model that we use is based on the lower bound theorem of plasticity. What does the lower bound theorem of plasticity states? It states you have your structure, okay? And if you are able to find a distribution of stresses in the structure, which is under equilibrium with the applied external loads. First condition, the distribution of stresses must be under equilibrium. And second, it must nowhere exceed the bearing capacity of the materials that the structure is made of. If you are able to find this stress distribution, the load corresponding to it is a lower bound approximation of the true failure load. Lower bound, because actually you may find not only one distribution of stresses, you may think of many of them. But whatever you find, anytime you find the lower bound approximation of the true failure load. This fact that it's a lower bound approximation is very important, because it means that we are on the safe side. Because if we would have found an upper bound approximation, we could not have accepted it, because upper bound means that it can be the failure load, but can be also higher. And if you're designing for something that is higher than the actual failure load, you are not on the safe side. So the fact that we base this model is based on the lower bound theorem of plasticity, means that it is on the safe side and we can apply it. Then, as I said, we can find different arrangements. Which one is the most probable? Most probable. The one which guarantees you the minimum energy. And minimum energy is, you know, the stress state times the deformation times the length. So for this reason, I said choose the path with the shortest length, because that is one condition to minimize the energy. Well, this condition also implies that the chosen stress is the most stiff one among the possible ones. So this guarantees you in some way for serviceability. If it's the most stiff one, is the one which deforms less, and you can, you know, trust or hope that for the serviceability limit state will be okay as well. So you see, for example, here there are two possible ways of equilibrating that load, of designing that element. On the left-hand side, you have the path that we have already seen, but you can also say, okay, no, I want, for example, that I bring up these forces and then I design a reinforcement which hangs down the wall beam. It could be possible. It could be absolutely possible. But in this case, you see that the length of the elements and hence your energy and your deformability is much higher. And so this is a bad choice. Well, this is also a bad choice from the constructability point of view, because it will require that you detail the reinforcement like this. You have to anchor the reinforcement and so on. You can also have some models with inclined reinforcement. Why not? We will see some examples after that. But now, okay, then we will see with examples, it's much more easy. But let us assume that we have understood how can we figure out the load paths according to which we design our strut and tie. Then we must understand how do we design the struts, how do we design the ties, and how do we design the nodes. And for the struts, well, for the ties, it's very simple. The ties are reinforcements. So if we have our strut model and calculate the force, then we know that the force is equal to the area of the reinforcement times its yielding strength. Very simple, the design of the tie. For the strut is concrete. But you know, concrete is everywhere. We must learn, we must understand how do we concentrate the stress fields into straight lines, or how the stress fields distribute so that we can identify the strut. So there are 2D or 3D regions depending on the thing. So you can see here some examples of how the compressive stresses, they distribute from this support to this wall width, or from this could be the case, for example, of a pre-stressing anchor. You have a concentrated force over a narrow region, and then you have to spread it to the wall cross section. And you see also, you understand here from this figure, you see these are reinforcement. Well, why do you put them there? Because the laser does not work. Look here, you have this force, and this force, in order to spread, it takes a curved path. Here it's vertical. Here starts going inclined. What does it mean? It means that it starts having a horizontal force. That horizontal force causes tensile stresses in the concrete. So this reinforcement is just to take those horizontal component of the stress which is distributing, which the concrete will not take because it cracks, and you must put the reinforcement there. So that is the reason, mechanically justified, for which close, for example, to a concentrated force, close to a pre-stressing anchor, we do put this confinement reinforcement, because we have to absorb the transverse tensile stresses which arise because of the diffusion of the compressive stress field. So we have three geometrical models that we can use to interpret the diffusion of the stresses. One is the fan here. The other one is the bottle. And if your geometry allows, is the prism. So the stress flows goes vertical. So here in the fan, you have continuous diffusion. In the bottle, you have this bulged shape. And in the prism, you have the regular flow. So in the codes, you find detailing recommendations. These are taken from the Euro code. So for example, you have here, a narrow column where its load could be a pre-stressing anchor, could be, for the support of a beam, you may also not rely on continuous. You just put a plate to distribute the load, but over a certain area, which is like this. So you have the width of this element, and you have the width of the applied load. And you see that, this is a typical reinforcement arrangement, which is recommended. And the T is the transverse tensile force. This formula comes from equilibrium, is the transverse tensile force that you can use to design this reinforcement. Wherever you have a very wide element, what is the area interested by your diffusion? Well, apply the same Descemet principle. You see, You never go wider than a certain collaborating width. But in this case, you see there is a reduction here. Because what? Well, you can rely on the fact that you have also a lot of bulk material around, which plays a favorable effect. So you do not need the same amount of reinforcement as in the other case. What? Equilibrium conditions are the same, but simply you have it's deliberately put because in this case here, you have a narrow area. So you are forcing your force to stay there and you have to rely upon only on the tie. Whereas here you have some confining material. So this could be, for example, the case of a excavation wall, excavation stabilizing wall, where you have these anchor points that are sufficiently spaced apart. But now we have to remember that, you know, in all these cases, you see, in all these cases, the material is experienced not a uniaxial stress of state, but is experienced a biaxial stress state condition or a triaxial one. And we were mentioning yesterday the studies by DJ Bellarbi and Thomas Su at University of Houston, the studies by Frank Vecchio and Michael Collins at University of Toronto. Look for the papers of these guys. Most of them are in ACI Structural Journal in the 80s or early 90s, I think. Very, very nice paper, fundamental papers for structural engineering in field of concrete mechanics. But the very first work on the biaxial and triaxial stress response of concrete was done by Kupfer, Hilsdorf, and Rüsch, 1969. I think it's ACI journal also, this one. They only had one ACI journal. Now they have two, structural and materials. And you see, these are some examples of, patterns. You have here a biaxial tension. And you see the resultant of the biaxial tension, what is a diagonal force. If they are equal, the resultant is at 45 degrees. And so you have a crack at 45 degrees. Yes, this is biaxial compression. This is biaxial tension. Yeah, it's the same. Yeah, you're right, because it's minus. Yeah. Then they ended up plotting their results in the form of an interaction diagram. Here you have, it's very. Here you have on this axis, the stress sigma 1 is in the vertical direction, divided by the uniaxial compressive strength, FC. And on the other axis, you have the stress S2 in the other direction, always divided by uniaxial compression. So if you move on either one of these axes, you have a uniaxial stress state. If you are applying uniaxial compression, your strength, what is that? Is the uniaxial compression strength. So you have one here and one here. This is the tension region. This is the tension compression region, and this is the compression. And you see that, well, the tension region is, very poorly defined. At that time also, in the 60s, it was difficult to perform tensile tests. But they said there is not much interaction between them. But in the tension compression region, as we were saying yesterday, if you have a concrete which is compressed longitudinally and you have lateral tensile stresses, you see that your interaction is negative because actually your strength is decreasing. And that is the reason for which, as we have said yesterday, in the shear design model, we use this factor Ni, 0.5, 0.6, more or less, according to that reduces the compressive strength. It's exactly because of this. When you have biaxial compression, you see the effect of biaxial compression is positive because you compress in one direction. If you confine, you actually increase a little bit, something in the range of 20%. And interestingly, the best situation is not when you have 1-1 ratio. It's close to 1, 2.6, 1, 2.55. Because if you have 1-1, you are already start engaging the material in both directions in the same way. So no direction can really fully help the other. This is very important. And the red one is the way in which we simplify this diagram. So we use straight lines here. And for the sake of safety, this 20% benefit, we say, okay, we neglect it. We neglect it, but we know that it does exist. And so, for example, if we have, this is the case in which you have a column or a wall where the elements supported above transmit the load only on a portion of it. If you have enough concrete, unloaded concrete around, you can rely, you can trust upon that concrete to provide some, we say, passive confinement. But if you do not have enough material, what do? We put the steel rooms, we put hoop bars to provide this confinement effect. This is the panel shear tester, and this is actually Frank Vecchio in front of it. This is a picture from the ACI journal at University of Toronto. So as I was saying yesterday, they formulated constitutive laws for concrete as a function, multi-axial constitutive law, one law as a function of the crack strain in the other direction. So in order to take into account the biaxial, let's say, stress states, for example, Schleich and Schaefer, which were the first ones to formulate this Strut and tie model. Also, there is a very nice paper of them. It was in 1987 in PCI journal, Journal of Prestressed Concrete Institute. Well, if we have uniaxial or even biaxial stress region, let's assume the strength is equal to the uniaxial compressive strength. As you see here, we always use the design value. We apply the Strut and tie model for ultimate limit state. So if you go back to the lecture of yesterday, it's the characteristic value divided by the partial strength, partial safety factor, times 0.85. So then, according to the transverse cracked state, they provided us 3 levels of, decay of the compressive strength. So if we have tensile strains with narrow cracks, 0.8, if we have inclined cracks, because the inclined cracks created higher disturbance, 0.6. If we have very wide cracks, 0.4. Well, but this is fine, this is okay, but still relies upon some kind of sensitivity. I think that Schleich died recently, a couple of years ago, more than 90-something years old. So, and still active. His engineering firm in Stuttgart is still active. So, okay, good. Then let's see how do the Euro codes, the codes, translate this, because this is a good formulation, but still relies upon the sensibility, the experience of the engineer, okay, which is good. So the Euro code says, okay, we have the main stress flow is this one, and transverse to it, we have compressive stresses. In this case, the maximum stress is equal to FCD. So we do not take into account the benefits that we know exists, and we do this because we want to be in sake of safety. So if we have transverse tensile stresses, reduce the compressive strength by a factor Ni, which is equal to 1 minus FCK divided by 250. FCK is the characteristic compressive strength in Newton per square millimeters. So what does it mean? It means that if I have a C25 concrete, this Ni factor is 0.9. And if I have a C50 concrete, 50 divided by 250 is 0.2. So this factor becomes 0.8. And if I have 100 megapascal concrete, this factor becomes 0.6. So it seems to be a strange thing. Say you have a better concrete and you reduce its strength more than if you have a worse concrete. Why is this? I hear some syllables that can be part of the right word. Brittleness. Yes, exactly that. Higher strength concrete is also more brittle. More brittle means that if you compress it, it tends to explode. A very, very explosive reaction. So a transverse tensile stress of state can be more, detrimental. The material feels in a stronger way. So you have to decrease its strength in a more severe way. Also consider that if you have a higher strength concrete, the sides of your strut can be smaller because you need less material to carry that strength. So can also be, if you have cracks, the solid part between the cracks, if it's very narrow and slender, can also undergo some kind of local buckling. There is a theory to interpret the failure of a cylinder under compression that says at a certain point, you have formed internal cracks which are vertical, parallel to the strut. So your specimen is no longer a cylinder, it's a series of parallel columns. And the more slender are these columns, the more catastrophic we say its failure in the sense of the mathematics. Now it comes a very nice concept, and yeah, for example, to design the lifting region, to design the lifting hook. Yeah, we have tension, so we assign the force all to the bars, and then we have to transfer this force from the bar to the concrete through bond stresses, and then likely, since these bond stresses they create some diffusion region, we have to provide some hoop reinforcement around. That is exactly an example where we can apply that. Now it comes this part which is a little bit, delicate, but it's how do we design the nodes? And the methodology that we used was proposed by Peter Marty in 1985. Peter Marty was professor of structures at ETH Zurich. Now Walter Kaufmann replaced him. So imagine that you have 3 struts, okay? And the axis of the struts are those where you have the forces FA, FB, FC. But when they meet, the node zone is made of these 3 segments, A, B, B, C, C, A. And they are not exactly orthogonal to the line of the strut. Orthogonal to the line of the strut is this dashed line, this line here, this line. So actually, we can say that we know the stress state on this dashed red line, but we do not know the stress state on the solid red line, because that is not the cross section of the strut. That is something inclined with respect. So how do? We know that on this line here, the dashed line, we have only one compressive stress, FA divided by the width of the strut that we have. We draw the Morse, and there is no tensile stress transfer. So we draw the Morse circle for that stress state. 0 stress in this direction. This stress here, sigma A. This inclination here, we report exactly here. And we find this point here, which is called the pole of the Mohr circle. The pole of a Mohr circle is a point from which, if you draw lines with any kind of inclination, and where you meet the circle, you find the value of the stresses for that inclination. So we want to know the inclination of the stress along this solid line. just starts from here and draw a line with the same inclination. You find this point. So what does it mean? It means that on this line here, you have a stress state which has a certain compression lower than this, but no zero tension. There is also some tensile stress. Well, it will be shear stress, but this is principle. Yeah, you have shear stresses here. Yeah. Yes, and we repeat. No. Sorry. Ah, okay. Yeah, very, very. I like it very much. I like it very much. So we can draw. I'm sorry, this slide is a little bit. We can repeat the same thing. We can repeat the same thing for the three struts, and we find these 3 points: A prime, A second, B second, and C second. When we have identified the stress states on this line here, on this line here, and on this line here, we have 3 points, and 3 points, you have enough then to draw another circle, which is this dashed thick flexor. That circle there represents the stress state in the node. In the node. So you find the maximum compressive stress in the node, the maximum shear stress in the node, the maximum tensile stress in the node, and you can design your node accordingly. I will try to look for the paper and share with you because it's a very nice paper. So we can apply this for the design of the node. And we do have different type of nodes. We classify them with letters. So we call these a CCC node. CCC means compression, compression, compression. You may have a node in which, for example, you have a vertical reaction from a support, and you have 2 struts arriving. So that is a CCC node. Well, actually, you have there the material under triaxial compression. Triaxial compression concrete works very, very well. But still in the code, we are a little bit cautious because we say, okay, we do not take into account K1 is the fact that you can have some benefits from multi-axial state of stresses. We put this one. But we still apply that, how to say, brittleness reduction factor. So for higher strength of material, under triaxial stresses, you may have at a certain point your concrete really crashes down, it pulverizes. So we take this into account for this. This is, for example, a CCT node. This is typical of a support of a beam. You have the reaction force, you have the strut coming, the first strut, and you have the reinforcement. So this is a C compression, T tie node. And you see the brittleness reduction factor is always there. But in this case, the biaxial stress state factor is a K2, which is 0.85. We consider that the tensile stress is disturbing our compressive stress flow. This is a typical beam column node. This is a frame corner. In the frame corner, we might have a TTC node. Because how do I go? This is exactly the detail that we have. So this is a tension compression node. And you see, we are further reducing the strength of concrete in this disturbed region. And then, okay, now we have the example, but I will skip this. Let's go. This is nicer, okay, because it also, okay, now it's 10:20. We have 10 minutes about, okay. So, okay, this is a deep beam. Okay, you see the deep beam has a span of 7 meters. And there is a load applied on the top is 3,000 kilonewton, means 300 tons, which is applied at 4.5 meters on one side and 2.5 meters on the other side. The supports and the load application area, they are not points, you know, because in the reality, your support has a physical dimension. And the same is for your load application area. So the supports are half a meter wide. And the load is applied over a 70 centimeter wide region. So it could be, for example, that this is a beam. Sometimes you have in buildings, you know, very deep beams, and there is a column coming not aligned. The top frame is not aligned with the bottom. You may have these in high-rise buildings. For example, you might have some stories, certain depths, where you host equipment for heating, for the lifting equipment, for cooling, for whatever, and they disrupt the facade because these are not regular floors. You do not have windows. They stay closed and so on. They are called technical floors, but you might. You also have a recess, opening into here, and this opening is 50 centimeter from the edges, and it's 1.5 meter wide. Okay. Well, imagine that you have a 30 megapascal compressive strength concrete. You have a 430 megapascal yielding strength steel, and the thickness of this beam is 40 centimeters. So first of all, which is the strut and tie model? Then the forces, then we design the ties, then we check the stresses, and then we design the rate. So the first thing is, okay, let us calculate the reaction forces. The reaction forces you calculate with the rule of the lever arm. You see, over 7, 2.5 is a little bit more than 1/3, and 4.5 is a little bit less than 2/3. So actually, over 3,000, you have that on this side here, you have more or less 1,000 kilonewton, and on this side here, you have close to 2,000. This is very simple. It's rigid body mechanics. You can perform some finite element analysis. And you see here, these are the compressive stresses. You see that the stress coming from the force, you have a major flow of stresses here. And then you have the flow that, in order to go to the other support, has to go around the opening. For tensile stresses, you see here, if you have these two struts coming here, the horizontal part of that strut has to find its equilibrium. If you have this two inclined strut coming here, the transverse part has to find its equilibrium. So the struts mainly connect the ties, mainly connect the struts. But now we have calculated how much RA and RB are. So let us divide our total force into two parts, RA and RB. And you remember we had this dimension here was 70 centimeters, whereas this was 4.5. So you see we have divided the beam in such a way the load finds its shear part RA on the left and its shear part RB on the right. Well, these two dimensions, 465 and 285, include half of the support on each side. Whereas if you look at the span here, actually the length of the beam is 7.5 meters. It's not 7. 7 is the span. You have 25 and 25 on each side. We do this because we separately design and analyze the right part of the beam and the left part of the beam. And we start from the right part, which is the easiest one. So how do we identify our struts? So we know, we have said, and we know that the part of the applied load which pertains to this right part has to go from the load application to the support. But actually, where are the nodes, the starting point of the struts and of the ties? Well, we make this very simple assumption. We say, how wide is this? It will be about 2/3 of 70 centimeters. So let's say 50 centimeters or more or less like that. This force is applied at the center. We just go down of the same quantity. And here we do the same. Here we do exactly the same. So when we have identified these 2 points, this is half a meter, half is 25 centimeters. So just go up 25 centimeters here. So this allows you, when you have identified these 2 points, this allows you to draw the straight line which corresponds to your strut and find its inclination. And then it's a very simple thing, because if you know RB, you write the node equilibrium, you find N1 and C here, you know N1, and you find N1 and T. That's very simple. That is what we have said there. On the other side, we try to do one thing. Well, actually, this is already the outcome of the design. You see here, it's not written 0.5 RA. It's not written RA, it's written 0.5 RA. So you can say, well, why I am designing for half the force? Because this comes from the paper of Schleich and Schaefer, actually. If you design for the wall force, you end up with some impossibility of designing your strut and tie mechanism. You will end up with a lot of reinforcement that you cannot match inside. So what the engineer has said, okay, he said, okay, let's try to pick up half of the force and design for this global mechanism. Well, this force here has to go straight to the top. The position of this force, you already know. Position of this force, you already know. Then it's a choice of the engineer to say, okay, I will put my tie at 45 degrees at a certain distance from the corner so that it is undisturbed. So this is a choice of the engineer. You may not have everything codified and written. There is a moment in which you must make your choice. And as structural engineer, you are responsible for that choice. That means that you put the signature under that. So he made this choice. So if you have 45 degrees and you align this, straight, this inclined line, you will find this intersection point because you know this position here. That position here is exactly this. It's the same force which has to go from one side to the other. You find these 2 points and you symmetrically locate your other struts. Well, half of R, it will be assigned to another mechanism. I will show it later. So he decided, because it's important, he decided to pick up the force and to assign to 2 different mechanisms working in parallel. Why did he not choose to assign everything to this model? Can you look at it, besides the fact that probably ended up with something which was impossible, but can you look at it? What is, if you look at it, one of the drawbacks of this model? That it has very long struts and ties. You see, there are just 3 of them, and they are very long. So the energy associated to this can be a deformable, a very deformable mechanism. So since he could not avoid this mechanism, because this is the most natural way the structure will behave, he tries to have it, he because it was Schleich, okay, to have him working for a lower force, so to compensate for the higher deformability. And this is the other mechanisms to which we assigned the other part. Well, here I have to say the creativity of a very expert, a master of reinforced concrete came out. But if you look here, let's try to, you look here, yeah. You see, you have here this compressive stress flow, and here you have the tensile stress flow. So actually, you see that there is a region in which these tensile stress flows are distributed. So that is the reason for which the structural designer ended up figuring this mechanism. Well, this is a little bit more, not complicated. Simply, you have to do more calculations to find the forces, but it's okay. So you can have this. This is important. This is the reason for which I say it's not only that you make the finite element analysis and then draw the lines and say, this is my Strut and tie mechanism. You also can steer the structure to behave in such a way. So what the structural engineer decided to do here was say, okay, take this force RA and have it to be subdivided between two mechanisms working in parallel because the sum of the forces give you the same thing. Yeah, and the previous one does not have edge reinforcement. Yeah, that's it. Yeah, this covers the reinforcement here. That is another reason for which, because we know that from the corners you have cracks, going up more or less diagonally, and this is what this does. But you know also that you cannot leave. This is another good point. You cannot leave the hole completely unreinforced just with 4 bars and 4. So things have to put some reinforcement here anyway. Let's use it. And let's do it. And so this is the global mechanism called design. So there are some, so now let's put some numbers. The tensile force here and in order to resist force applied by the yielding strength find the area, well, check the stress here, divided by this area, find 7.65 or 30 megapascal strength can stay below FCD for a you also check that the see that the stress of I and on how to reinforce how they did it art of reinforcement. See another interesting thing that so he said that we need 12 actual figures. But why? Because he has 4, 5, 5, and 4. Actually, the 10 central part at a certain point where you do no longer need them. Well, so you continue. This is also a now this is 7 meter long. That 2.5 meters, something like that. And this was 4.5. 4.5 multiplied by square root of 2, which is 1.4 is 7 meters. 7 meters plus 0.5 and so on, it's around 10. Consider that the steel bar is 12 meters long. So one task, right? First of all, well, but the other thing is not to have too many broken pieces, because if you have half a meter chunks, when this brings to project, always like steel, like a 10%. So, so leftover. So a good thing would also be to try to see, okay, when I design my rainforest, how many leftovers? If I have 7-meter bar long here, can I have somewhere else 5-meter bar that I use cutting the 12-meter long? So this is, I think that I have of this paper, right? So it's a very old paper, and I don't think it's available in the digital archive of the I have PDF, but PDF photocopy of my old paper copy. But I will look at it and I will share. Yeah, that this does not have anchors here. But what you can probably do, you can probably anchor them in the horizontal way. So you make some kind of hoop, and you do not have enough length to make a continuous one. But you can probably have possibility anchor. What you also either bend up, but if you bend them up, you will have too much congestion. So you can, anchor that in the horizontal way. Well, at a certain point, it has become also common to use fuzzy logics to draw the best strategy. So this was a method that was developed by some colleagues in our department. So they simply discretized their domain and they randomly connected to identify all the possible, and through a Monte Carlo simulation, they identified the one with the least associated. But nowadays it's very common in 3D printing that you 3D print the material according to topology. But the funny thing is that this is the Strut and tie mechanism which comes out from fuzzy logic, which is not much different from the one that we have seen it was designed before. Well, actually, here I acknowledge my colleague because he helped me quite a lot in preparing these slides. It's Professor Patrick Mamonte, and he's very, very expert in Shu and Bellarbi and Vecchio and Collins methods for designing structures.